Okay, welcome to Advanced Aerodynamics. This is the first lecture for Chapter 1 and 2. What I would recommend that you do is get your book and follow along as I go through the lectures during this course. This is an 8-week course. There's a good amount of material to cover, so I'll do my best to highlight the important parts out of each chapter. But it's really up to you to look at the chapters, read the chapters, and ensure you do the problems in the back of the book. So let's go ahead and begin. You'll see on page 1 in chapter 1 some measurements for force. We're going to use the US system is going to be in pounds. Distance will be in feet. And time will be in seconds. And then if you look below that, you'll see velocity is in feet per second, which sometimes we'll refer to as FPS. Area is in feet squared. And pressure, pound force, we're going to be in pounds per feet squared. And then acceleration is going to be feet per second squared. So make sure you understand those things as we go through. All right, let's look at the next thing as we look at forces. One of the things with forces that's important to know, and you're probably familiar with forces, is we need two things to know about the force. It's the size of the force. Sorry, let me get this. Size and direction. So 40 pounds, and then whichever direction the force is acting upon an object. The second thing, if you look on page 2, we start to look at the various aspects of how forces act upon an airplane. So I'm not going to spend a lot of time on trying to draw a specific airplane, so let's just do something very simple. If you look at figure 1.1, you're going to see it broken into weight, thrust, and then the aerodynamic force. The aerodynamic force we can break into two things. We can break that into lift and drag. Okay, and this is important because when we start looking at vectors and scalars, we're going to have to add these vectors to try to make sure we understand how vector addition works. So if you look at vector addition, and we say we have an aircraft, V of AC, going at 300 knots, so that's the size, and here's the direction. And then we say the airplane encounters a 30-knot wind, so we'll look at that at this, and then this is the direction. So if we draw these, we would draw V of AC this way, the head component this way, and then if you took a line and draw from the tail of the aircraft speed component to the wing component, this is what we call our resultant vector, okay, or vector resolution. So if an aircraft is in steady climb at constant airspeed and climb angle, the ground speed and the rate of climb can be found by this vector resolution. So very similar if we climb angle. So here's the horizontal component and the climb angle component, and this would be angle of attack. You also see pitching moments. So if we pull back on the control stick, this is going to cause the elevator to move upward, and the downward force on the tail is what's going to result. So if we draw an airplane here with an aileron, and let's call this my stick, and I'm going to pull back on the stick, so now I have this, so I'm pulling back on the stick. The elevator is going to move up, And if the elevator moves up, there's going to be a downward force that's going to act upon the tail surface, okay? And then the nose is going to pitch this way, and we call this a pitching moment. The moment arm is the distance from the force. So if we knew the force was acting here on the elevator, and this is the nose of the airplane, this is some time of distance. So the moment is going to be equal to distance times the force. And that's how you're going to get pitching moment. And this is going to be in foot-pounds, because this distance is normally in feet, and this force is in pounds. So that's how we get foot-pounds. So anytime you see a moment, it's going to be represented by foot-pounds. The other thing that we'll say when we're looking at an airplane: lift, weight, drag, and thrust. If all four of these forces are equal to each other, this is in equilibrium. Okay? As soon as we do some type of perturbation on the airplane, pitch up, pull down, speed up, slow down, we've changed equilibrium on the airplane. So this is important when we look at there's three laws known as the laws of motion. And we have the first law of Newton. It says a body at rest will remain at rest, and a body in motion will remain in motion in a straight line unless it is acted upon by an unbalanced force. So this is a good representation of an airplane trimmed out at straight and level flight. Okay? When you're in equilibrium, all these forces are equal to each other. This is a good example of Newton's first law. Newton's second law states if an unbalanced force acts on a body, the body will accelerate in the direction of the force, and the acceleration will be directly proportional to the force and inversely proportional to the mass body. So a good example of this is, again, let's draw the airplane. So lift, weight, drag, and we have a huge thrust component, okay? So we're accelerating in the direction of the force. And this directional, there's going to be something acting proportionally back onto the airplane. So what happens is, as thrust increases, drag will also increase. So it's important to know aerodynamics. So if you look at that in the second law, we normally represent that by force equals mass times acceleration. So this is important to know. And then for Newton's third law, this law states for every action force there's an equal and opposite reaction force. Okay, so this is important to understand. Basically very similar to if you hit the brakes on an airplane or if you fired a gun. The recoil of the gun is going to be that equal and opposite reaction of the bullet exiting the weapon. Look at mass, work, and energy now. Weight is equal to mass times gravity. So if we know weight is equal to mg, and we know mass then is equal to weight divided by gravity. And we give this name slugs, which is slugs represented by, if you want to know what the units are, pound, second squared divided by feet. But to make it simple, we just say 4 slugs, 5 slugs, etc. All right, let's look at energy. We have two types of energy. We have potential energy and kinetic energy. Okay? Potential energy is equal to the weight of an object multiplied by its height. Okay, so if I had a tennis ball and I wanted to calculate the potential energy of this tennis ball, I would first weigh it, how many ever pounds it is. And it's going to be very small, so let's just say 0.4 pounds. And I'm going to drop it at a height of 5 feet. This will give me the potential energy of the tennis ball. Okay. I'll look at kinetic energy. It's going to be equal to 1/2 mass times velocity squared. Okay. And if I want total energy, it's going to be equal to potential energy plus kinetic energy. And this will give us total energy of a object. If you look at power, power is really a combination of both work and energy. And power is equal to work divided by time. However, we know distance divided by time is equal to speed. Okay? And then horsepower, HP, is force times speed divided by 550 foot-pounds per second. Okay? If airspeed is measured in knots, which will represent, as the book does, in VK, horsepower is going to become this. It's going to be equal to thrust times VK, which is airspeed, okay, divided by 325. So you're probably wondering where 550 and 325, they're constants. If we did an entire derivation of horsepower, we'd show you where these constants come from. But just assume that's the constant you use when you want to find horsepower. Thrust times airspeed divided by 325 will give you horsepower. All right, finally we'll look at friction. Friction is really important, especially when we look at aerodynamics. Reason is on airplanes, laminar flow across the surface area. So airflow flows across here. There's friction that occurs. Okay. Also in tires and hitting the runway, there's friction here. So friction is really important in aerodynamics, especially when we look at laminar flow, turbulent flow, and brake distance, brake speed, that type of thing. Friction force divided by normal force is a constant. And we use a lot of constants in aerodynamics because it's easier for us to do calculations. And these constants have been derived based off of a lot of various things, various airfoils, and also based on standard atmospheric pressures, international standards for aerodynamics, which we'll get to in the next lecture. If you look at page 11 on figure 1.8, mu is the coefficient or the symbol we use for determining friction. So if you looked at figure 1.8, you can see a coefficient of friction of 0.2, and then the percent of wheel slip in heavy rain. You can see it would be roughly 7% in heavy rain for friction. So coefficient of friction are reduced and braking distance are increased. So if too much brake pressure is applied, the brakes will lock and the wheels will stop rotating. And this happens as the tires skid and rubber is melted and separates from the tread. Besides the possibility of causing a blowout, the coefficient of friction is reduced and braking distance are increased. So you can see in the graph up top, coefficient is really high on day concrete, and then it gets much smaller as you look at ice. So smooth, clear ice, you can see a coefficient of friction is extremely, extremely small. So we want a higher coefficient of friction, and this is important when you're landing on ice or rain conditions. All right, I think that's it for Chapter 1. We'll go ahead and start Chapter 2 here in the next lecture.